Today, my little Padawans, we're going to continue by simplifying trigonometric expressions, but this time we're going to be using new formulas. We're going to be talking about the trig identities. So this time we're using double and half angle formulas. And let's just jump right into it with an example. Our job is going to be to verify the identity. And example 1 is cosecant. Cosecant of 2 theta equals the secant of theta over 2 times the sine. All right. What do you guys notice? There's something that's different about this problem that we haven't seen before. It's very, very subtle. Can you see what do you think here? Oh, yeah. Now this thing is a little more complicated. This is kind of like when you have, if I said something like x plus 3y. Right? You can't really simplify that. I'm going to erase this in a second. But you can't really simplify that, right? Because they're not considered to be like terms, right? You can only combine x's with x's and y's with y's. So here, I can't start simplifying any of this. I can't compare the left side to the right side until both of these are talking about either theta or they're both talking about 2 theta. But I can't have one side talking about 2 theta and the other side talking about theta. And no, I can't just divide both sides by 2 because I'm not allowed to separate the angle from the trig function. I got to treat this as one big group, right? So in order to do anything with this problem, I have 2 choices. I either need to convert, I need to convert either 2 theta to theta, or I need to do theta to 2 theta. But somehow I got to get them all using the same terminology. I got to all use the same angle here. All right. Right now, you don't have what it takes to solve this problem, so we have to equip ourselves with a new formula. So I introduced to you the first of, I think we're going to do 4 formulas today. This is what we call the double angle formula. It's one of them anyway. And this says that the sine of 2 theta equals 2 times the sine of regular theta times the cosine of regular theta. And I'll go ahead and give you the second one now, which is the cosine. So this is the second one. Cosine of 2 theta equals cosine squared minus sine squared. Now, those are what we call the double angle formulas. Now, just so you guys know that I'm not feeding you some bull hooey, right? There's always a way that you can verify. You know how a lot of times you like to check your answers if you got extra time at the end. You can check to see if this is true or not. And one way you can do it is you can go into the graphing calculator and put, I guess, the recorder won't see me hold up my hand like that. So You can put this side of the equation into y1. Put this side of the equation into y2. When you graph them, if they're really equivalent, your graphs should, what should they look like if they're equivalent? They should be the exact same thing, right? So I don't know what this graph is actually going to look like, but no matter what they are, they should lie on top of each other when you do it. So if you go to y equals, let me just reset the timer a second. 7, 1. And I go to y equals. And so we put sine of 2x. And then it's the formula says that that's the same thing as 2 times the sine of x times the cosine of x. Now I'm going to make the first one regular font. I'm going to make the second one bold. Actually, you know what's kind of cool? Let me do. Oops. You guys know you can. There you go. I'm just going to pass a ball over the second one. So the first one's going to come in normal, and the second one is going to. There's a ball that's going to come out and trace where the line is. So hopefully, the ball will trace the line that's already there. And then you see how it kind of goes over pretty quick. All right. So that's the way it's showing that these two lines are actually right on top of each other. If you do it like that, go to second table, and you'll see that you get the exact same value no matter what the x value is. Okay. So that's a good way you can check your work. Like if you're done with the test, put the left side in as y1. I'll put the original, and then put y1. Put the you can simplify it as y2. Wrap them, and they should lay on top of each other. All right. So there's a new formula. Now, let me go ahead and give you a little hint on the cosine one. You see how that's almost like the Pythagorean identity? The only difference is instead of cosine squared plus sine squared, you have cosine squared minus sine squared, right? So what that allows you to do, it allows you to make two other identities, which might be a little easy, or which might be more helpful down the road. So here's a little thought bubble. Think of the Pythagorean identity, which says sine squared plus cosine squared equals 1. If you, let's see, how do I want to write this? Okay. If you trade out a cosine squared, like say I'm gonna solve this guy for cosine squared, so then I'll get cosine squared equals 1 minus sine squared. Then I can trade out the cosine squared over here with 1 minus sine squared. Can you see how if I do that, you might not want to write down the original part, but you're going to see the transition here. I can replace that with 1 minus sine squared minus sine squared. So if I combine my like terms, can you see how that's going to end up being just 1 minus 2 sine squareds? You follow that? So I put in the 1 minus sine squared for cosine squared. Now I got 1 minus sine squared minus sine squared. That's like having 2 sine squareds, but they were both negative. So voila, I just made a new identity. So I just made a new identity. Now you can also do that if you solve it for sine squared. Sine squared equals 1 minus cosine squared. So if I replace this sine squared with 1 minus cosine squared, can you see how I'm going to end up with negative 1? Negative times a negative is going to make a positive. So I'm going to have cosine squared and a positive cosine squared. So that's 2 cosine squareds minus 1. So voila, I just made another identity. Sometimes you're going to want to be able to write these in terms of just sine or in terms of just cosine. So you want to keep these extra ones in mind too. Alright, so those are my double angle formulas. Can you tell why we call them double angle formulas? Okay. It's like you're doubling the angle and putting it in terms of somebody that is just a regular angle. Hip hip hooray. Now that we have our 2 new formulas, see if we can use them to help simplify this expression. Let me check the finish line. I'll give you guys a hint on where to start. I didn't give you a formula for cosecant of 2 theta, and that's because cosecant is just 1 over sine. So that's where I would start this thing. Talk to us. How did you end up with that?
Well, since I knew that cosecant is 1 over sine,
Mm-hmm.
the right side. So, and also I knew that secant is 1 over cosine theta.
All right, so replace the secant. You say with 1 over cosine. All right. Okay. Now what?
Then I used the double angle formula for sine theta.
Sure.
So I put sine theta minus cosine.
All right.
And also, like, about everything else,
Okay. All right.
and I showed it for like the right side, left side, and I just multiply the right side with both sides.
Oh, so you did you did a cosine up here.
Use both sides for left side.
Oh, you multiply both sides by the cosine. You can do that. It's a little dangerous. Normally when you're simplifying these, you don't ever need to cross over the equal sign. So, because sometimes what happens is you're going to end up doing something illegal. Like here, when you multiply by cosine, it's not that big a deal. But like if you were trying to divide by cosine might end up being 0, depending on what the angle is. And you're never allowed to divide by 0, right? So instead, what I think might be a little easier, here I am, I got 1 over cosine. I'm dividing by 2 times the sine of theta. You guys okay if I write that as a fraction? Like just throw a little 1 under there. Dividing by a fraction is the same as multiplying by the reciprocal. Okay? Yes, no, maybe so. So now 1 times 1 is just a 1. Cosine times 2 times the sine is just 2 times the sine. That's cosine. So then your right side also equals. Now the left side equals the right side. And we go. So the trick there is when you get to this, you have the fraction within a fraction thing. That's probably the hardest part. Really, you can kind of think about this cosine just gets pushed down into the denominator, or you can rewrite it as a fraction. And remember that dividing by a fraction is the same as multiplying by the reciprocal. How's that? Not so bad? Well done, Mr. Dunham. How about another example? Ejemplo 2. Let's do. That's, oh. Um, 2 cosine squared. It's recording, isn't it? Yeah. 2 cosine squared of theta over 2 equals 1 plus the cosine theta. All right, same idea. We're trying to verify this identity. That's some nasty problems. All right. So, should come as no surprise. What's different about this one? Theta over 2. Not a double angle this time. Instead, guess what we're going to call this formula? A half angle formula. So I got a couple new rules for you. Half angle formula, we got 2 of them. First one says that sine of an angle cut in half equals, and these are kind of funky, plus or minus the square root of 1 minus cosine over 2. That's nasty. Yep. That's nasty. Now the plus or minus thing is going to play a bigger part when we start solving trigonometric equations. And then let's see here. Cosine of theta over 2 is very similar. Plus or minus all over 1 plus the cosine of theta all over 2. Again, let me just divide these so we don't get confused. And let's throw a magic box. This is my double angle half angle formula. And just like before, if you really don't believe that that's true, you can always graph the left side and graph the right side, and those 2 graphs will line up right on top of each other. So you know that they are equivalent. I don't think you guys really need my help on this one. I meet you at the finish line. Hit it. Break it down for us, Will. What's going on?
What I did was I used the second angle formula.
Sure.
Left side.
All right.
And because it's cosine squared, that cancels out the square root.
All right, hold on. So you're saying that, so I replace the cosine theta over 2, replace him with plus or minus square root of 1 minus the cosine of theta over 2, but, yeah, sorry. But we were squaring that whole cosine. So that means because I was squaring the cosine of blah, 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 I'm going to square all of this, blah, 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 blah. So when I square that, the square root and square cancel out. I heard some people asking about the plus or minus thing. Anytime you square something, whether it's positive or negative, doesn't matter. It's always going to come out to be positive, right? So basically that square root sign just gets canceled out. Aha. Still have the 1 plus cosine trait over here. Twos cancel out. And you end up with 1 plus cosine equals 1 plus cosine. And that is exactly left side equals the right side. So we're happy. Que fácil, no? Muy fácil. It's just a new formula, but it's the same idea. Just substitute a few things, and you're looking to make the left side equal the right side. Not bad, right? Not bad at all. All right, last example for today. Ejemplo 3. Sine to the 4th power of an angle minus the cosine to the 4th power of that same angle equals 2 sine squared minus 1. Yeah, we still got the same rules in play. Now you notice, no angle is getting doubled. No angle is getting cut in half. So why would we talk about this example today? What do you think, Will? Yeah, the 4th power, we haven't seen that before. Maybe that's something different. If you double the double, you get 4. However, that's not, notice guys, these fourths, they're not going to the angle. They're going to the whole. So once you take the sine of some angle, then you would take it to the 4th power. It's not saying the sine of some angle to the 4th power. See the difference? That's why they write the exponent in the middle, to avoid that confusion. If they wanted to do that, it would look like this. Okay, and they probably put parentheses around it, just so there's no confusion. But there's something that eventually we're going to have to use one of our new formulas here. But right now we can't actually see it. But that's okay. Let's go to work. Sine to the 4th power minus cosine to the 4th power. Yeah. We haven't talked about any identities that have anything to do with the 4th power. So what could we possibly do to try to bring those exponents down to something that we are familiar with? Square root? If I just take the square root of both sides, if I do that, will that just simplify down to sine squared? Am I allowed to do the square root across a minus sign like that? No, if you do, I'll cut you. No, I won't cut you. But, yeah, I don't have to edit that out. Well, we won't, there'll be no cutting. Remember, you're not allowed to just cancel out. If it said times, then yeah, you can do the square root of both sides. But not if it says minus. So no, I can't just do the square root of both sides. Good idea though. What do you think, Will? The Pythagorean identity would be great if these were plus. But it's not plus.
The inverse of Pythagorean.
It's minus. Say again? No, it doesn't work like that. So what else could we do that could reduce those 4s down to like squares? Would be real nice. Starts with the F, rhymes with tractor. You could factor. Oh my goodness. Think about our favorite factoring rule, difference of squares. If I have a squared minus b squared, I can factor that into a plus b times a minus b, right? Well, think about sine to the 4th as sine squared squared. And think about cosine to the 4th as cosine squared squared. So that means I can factor this into a plus b times a minus b. So my a is sine squared, my b is cosine squared. And it would look a little something like this. Haven't done diddly squat with the right side yet. So that is still, you know. Oh. Now we got the Pythagorean identity, right? Sine squared plus cosine squared we know is equal to who? 1. That's the easy one to remember. Second Pythagorean theorem. And then I end up with sine squared minus cosine squared. Alright, still haven't done diddly squat with the right side. Whatever shall we do, Mr. Horner? Oh, you're on the right track. Something to do with it. Look at that right side. Does that right side look familiar? 2 times the sine squared minus 1. What do you think, Will? Oh my goodness. It's almost one of the double angle formulas. Not quite. I think Mr. Horner had it hit on the head. He was like negative cosine. I think he said 2 cosine, which you know is cosine of 2 theta. Whatever. Yeah, right. So if you look here, you see how we have 1 minus 2 sine squared, but this says 2 sine squared minus 1. Remember that old trick that says, kind of like key flip change, if you have A minus B, but what you really want is B minus A, then you can take B minus A if you throw a negative in front. So that means over here, I know this is going to equal cosine of 2 theta, but I got to throw a negative in. Now, if you want the step-by-step on that, really what we did was I put a negative so that I can switch this around. And now, if you use your double angle formula, 1 minus 2 sine squared is the same as cosine of 2 theta. So I can replace that with cosine of 2 theta.
You don't need to flip side.
Now, you don't really need to place it because there's only one thing over here. Like it's just, once you break it down to cosine 2 theta, and then that's now over here, ooh, sine squared minus cosine squared, that looks familiar too. And if I go over back to my double angle formula, it's almost the rule for cosine 2 theta. Same idea, we can flip these around if I pull out a negative. So then really I can change this to negative cosine squared minus sine squared, which is really the same as negative cosine 2 theta. And the left side equals the right side. Hip, hip, hooray. Que fácil, no? That one was tricky. You had to get a little funky on that one. You had to get a little funky. Alright? And then keep in mind, guys, you can always check your work on this one, I guess. You can graph the left side, graph the right side, see where they line up. Alright? So you are now perfectly equipped to handle your homework, which I will now pass out.